Hi, it's John Williams here at MIT. So I want to go over the basics of public key infrastructure, PKI. And the basics lie in mathematics. And let's suppose we have a length of rope. And we know that it can wrap around the clock maybe once or twice. It looks like about twice. And then we'd have some remainder here that it would go 2 whole times, and then maybe we'd end up with a 4. So what we say is the modulus of this number, so the length of the rope might be a number, let's suppose it's 41. So in that case, it would wrap around 3 times, 36, and we'd be left with 5 to get us to 41. So we'd say the modulus of 41 to base 12 is 5. So in this case, we know no matter how long the rope is, it's going to have a modulus between 0 and 11. Yep. So if it gets to 12, it's going to be the same as 0. If it's divisible by 12, so 48, for example, would be 0 in modulus arithmetic. So let's take a look at Fermat's, what they call his little theorem for n prime numbers. So let's suppose we have modulus here p, and let's suppose p is a prime number. So here we have the numbers 1, 2, 3, 4, 5 up to p minus 1, and we know that those will not divide into p. Yep, because p is prime, so none of these will divide into p, and that these would be all the numbers that we could get. We're going to exclude 0 for the moment here, but these would be all the numbers in the modulus p arithmetic. So now Fermat did a very clever thing. He said, let's multiply by a number a, but a mustn't be divisible by p or share a factor with p. So since p is prime, we choose that p must be prime. Then, so for example, let's choose p as 5. So the set of these numbers would be 1, 2, 3, 4. And let's suppose a is 2. So in this case, we'd have 2, 4, so those already, that's in this setup here. Then we'd have 6, but in modulus arithmetic, 6 would be what? If we're doing mod 5, then it would be 1. And then we'd have, the last one would be 8, and that would be 3. So we'd have 2, 4, 1, 3. Notice that these are the same numbers in S, but just arranged in a different order. And Fermat used that. He said, let me show that for any prime p and any a that is not divisible by p or doesn't share a factor with p, then any q will just be the same as S, but in a rearranged form. Let's see if we can prove that. So here, let's first show that q of a isn't 0 mod p. So it's not 0. Well, we know that a is not divisible by p, right? Because we chose p as prime and not sharing a factor with a. So a is not divisible by p. And k lies between, k is one of these numbers, so it's less than p. We have it either as 1, 2, 3, 4, 5 up to p minus 1. So we know that none of these are 0 in modulus arithmetic, mod p. So now let's show that all these elements are distinct. So suppose we have an r that lies between 1, 2, 3, 4, 5 up to p minus 1. and an S. And let's suppose they're not the same. The R and the S are different. So we know that we don't get 0. So R minus S is not divisible by P because both R and S lie between 0 and P. And we know R minus S is non-zero. So if R, A, and SA are both distinct, that means, and they must be distinct, that means that all of these elements in here must be, in modulus arithmetic, must match the elements in S. So they just must be in a different order. How can we use that? So every element in Q is distinct and must be just a rearrangement of S. So let's take the products. So back here, let's multiply all these together. In S, we're just going to multiply 1, 2, 3, 4 up to P minus 1. And in Q, we're going to multiply A times 2A times 3A up to P minus 1A. So if we take the products, we know for 1 times 2 times 3, that's just P minus 1 factorial. Now on the other side, we've got how many A's in Q? Well, we've got A to the P minus 1 of those A's, and we've got factorial P minus 1 again. And all this is in mod P arithmetic. Now, we can divide by P minus 1 factorial because we know it's non-zero and it's not divisible by P. So we can divide this side and we can divide this side. So now we get A to the P minus 1 is in mod arithmetic 1. And we can express that slightly differently, that A to the P is A mod P. Now we can use that in encryption. So let's see how we might use that. Notice that we've got an A here raised to the power that somehow, we've got an A here raised to the power P that in modulus arithmetic gives us A again. That's kind of interesting, but let's see how we might use it. So suppose we can find some encryption. So here I'm saying m raised to ed, the power e times d, so to some number, mod n, would give us m again. Now if m was a message, say 89, we might be able to raise 89 to a power in modulus arithmetic that gave us m again. Now that would be really interesting because let's suppose here the encryption part, let's just take m to the power e. So m is what we want to encrypt. We raise it to a power and take the modulus of it, and we get some encrypted message c, some encrypted number c. Now the decryption part would be we'd raise c now to the power d. So up here, for example, yeah, now we've got it, and mod n, what would it give us? Well, c is m raised to the power e, and now we raise it to another power, d. So that's just m raised to the power e times d, which we've got up here. And modulus n, we know it gives us the message m again. So Fermat's theorem could possibly allow us to encrypt. Now the only thing is, can we show that this is true? We showed in Fermat's theorem that m raised to some p minus 1, or rather p, gave us m again. But we need to do a little bit more work. Let's see. I'm going to come back and do that in another video. So let's just stop for now.